Welcome back. Let's now throw into the mix the addition principle. And this is telling us that if you've got an event that has a finite number of outcomes, and again, in this class, everything will be finite. So we've got an event E, and it has K different things inside of it. Outcomes are E1, E2, all the way up to EK. If you are interested in E happening, then you're interested in either E1 or E2 or E3 or. You're interested in one of those outcomes happening. And just as a reminder, for outcomes, when one is happening, then the other ones are not. So there's no way that you could have more than one outcome happening at a time. So I don't have to worry about overlap. I don't have to wonder about what happens if E1 and E2 are both happening, because I know that that's not possible. So really what it boils down to is just inclusion exclusion, because if E is happening, then one of these outcomes is happening, E1 or E2 or E3 or E4 and so on. And we know for inclusion exclusion rather, the probability of a bunch of things connected with or really boils down to addition, so that the probability of E happening is just the probabilities for the individual outcomes all added together. Okay, let's do an example. And we've returned to our candy dish where we've got our different flavors. And this time the probability distribution table is filled in completely. We have all of our outcomes with all of the associated probabilities. And we're interested in the probability of E happening, which is the probability of us selecting a citrus fruit. Now, citrus fruits are, in this case, oranges and lemons. Those are the citrus fruits. The grape, the cherry, the banana, they're not citrus. So if we say probability of us selecting a citrus fruit, we are interested in us selecting an orange or a lemon. So that's the probability of us selecting an orange plus the probability of us selecting a lemon. And orange probability is 1/17. And lemon's probability is 3/17. So to get an orange or a lemon, in other words, to get a citrus fruit, should be 4 out of 17. Now, up till this point, I've only just given probabilities inside of a probability distribution table. At this point, we're now going to start to calculate probabilities for ourselves. Before we do that, though, we just need to introduce the idea of a uniform sample space. And all that is a sample space where all the outcomes are equally likely to occur. We've seen lots of those already. So rolling a six-sided die and seeing one of those six numbers, all six numbers are equally likely to happen. That's a uniform sample space. Selecting a card at random from the deck, each of the 52 cards is just as likely to be selected as any of the other ones. That's a uniform sample space. So good news, if you have a uniform sample space, then any outcome, the probability of it occurring is just 1 out of how many outcomes do you have in total. So if we were interested in selecting a card from the deck, then for any card in the deck, it should have a 1 out of 52 chance of being selected, since there's 52 cards in the deck and they're all equally likely. Now, if you have an event E and you're interested in the probability of it occurring, using the addition principle from before, you'd say, well, E has however many things inside of it, and each of those things has a probability of 1 over the sample size. So if I wanted the probability of E, essentially it boils down to just a counting problem. I just need to know, well, how big is E? How many outcomes are inside of it? That will be my numerator. And then how big is my sample space? That'll be the number of things that are in the denominator. So if we're thinking back to the card selecting problem, if I'm interested in an event where there are 2 cards in question where that event will happen, then the probability should be 2 out of 52, since there's 2 successful outcomes out of the 52 in total. Okay, let's put this into practice with an example. And conveniently enough, we are selecting a card from a standard deck. This is a uniform sample space. If we're selecting a card at random, then any one of those 52 cards should be equally likely to be selected. So I'm just going to make a note here to myself that there's 52 things in this sample space. And now let's start answering the questions. We want to know what's the probability of us selecting a 7 of clubs. And I know to select a 7 of clubs, I would need to count how many 7 of clubs there are in the deck out of the number of things in the sample space. And there's only one 7 of clubs. So probability of selecting the 7 of clubs should be 1 out of 52. If we want the probability of selecting an ace, I need to count how many aces there are in the deck and how many cards in total. There are 4 aces in the deck: ace of hearts, clubs, diamonds, and spades. And there's 52 cards, so the probability that you will select an ace, 1 out of 13. And then finally, selecting a red queen. So to select red queens, I would need to know how many red queens there are in the deck and how many cards there are in the deck in total. So we have 52 cards in the deck in total, and of those 52 cards, there are 2 red queens. There's the Queen of Hearts and there's the Queen of Diamonds. So the probability that you will select a red queen, 1 out of 26. Okay, let's do another example. This time we're tossing a coin 3 times. We are recording our sequence of heads and tails. And I know in advance, if I'm thinking about this, for flipping a coin 3 times, that's 3 little tasks. First flip, you have 2 options, heads or tails. Second flip, there's 2 options. Third flip, there's 2 options. There should be 8 outcomes in total. And so for part A, I'm interested in finding the probability distribution for this experiment, and the outcomes are going to be all the different sequences. There's 8 sequences in total, so let me write them all down for my outcomes. You could have heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay, so those are all the outcomes. And if I am flipping a coin, then each of those outcomes should be equally likely to occur. So for my probabilities, each of these should be just 1 out of 8. So 1/8 for all heads, 1/8, 1/8, 1/8, 1/8, and so on. Okay, so not too bad. That's our probability distribution for all the individual outcomes, where the outcomes are sequences. Now, I could take that same information and use it to create a second probability distribution. Because suppose that instead of me actually thinking about the outcomes being the sequences, maybe the outcomes might just be me counting. I might say, well, what if I instead of thought about sequences, what if I counted how many times did you flip tails? And so in that case, there's really only 4 options, because either you flip tails 0 times, or you flipped it once, or you flipped it twice, or you flipped it 3 times. So there's 4 different outcomes for this experiment. For this experiment, though, these outcomes are not all equally likely. Getting tails 0 times is not as likely as getting tails once or getting tails twice. These are not all equally likely, and the reason I know that is actually from my previous probability distribution table. To get tails 0 times, you would have to have flipped heads, 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 and we know that that probability is 1/8. To get tails exactly once, you would either need to flip heads, heads, tails, or tails, heads, tails, or sorry, tails, heads, heads, or heads, tails, heads. There's 3 different ways in which you could get a outcome where there's exactly 1 tail, and each of those has a probability of 1/8. So to get 1 tail should be 1/8 plus 1/8 plus 1/8. It should be 3/8 in total. And similarly, to get 2 tails, there's 1, 2, 3 outcomes where the possibilities are for 2 tails. And these all have probability of 1/8. So to get 2 tails is either 1/8, or it's this 1/8, or it's that 1/8. So probability of getting tails twice should be 3/8. And then finally, to get tails 3 times in a row, there's only one outcome where that happens. That's the very last one, and that probability is 1/8.